Okay, everyone. So today we are going to talk about encoding and image formation. This is part one in our MRI series. What you see here is a very basic pulse diagram. It's missing a lot of things, but you can see at least the line for the radio frequency. You can tell that this is a spin echo sequence because we have a series of 90s and 180s. We know that the TR goes from the 90 to the next 90, really from the excitation pulse to the next excitation pulse. And that the TE starts in the same place, but goes to not just the echo, but the center of the echo. We're also seeing the signal down here. It's not labeled, but this is our FID. We could see it's a very high, but half of a signal. We really generally don't collect these. There are some sequences that we do collect this data. However, generally speaking, we collect this echo here after it has been rephased by the 180-degree rephasing pulse. So we're going to talk about some of the mechanics and specifically some of the other magnets that we have in the actual MRI scanner. So I'm not sure why this kind of came off the screen here. So I'm going to try to fix this just a little bit. That should be better. And in order to do what's known as spatial encoding, we need to make use of the gradients. If you'll remember from a previous lecture, the gradients all work the same way. They flow a current through some wires. They can flow in one direction, a positive polarity, or in the other direction, a negative polarity. However, Faraday's law says this flow of electrons, so a moving current, will yield magnetism. So the gradients are like leaf blowers, and they can throw out a magnetic field, a small one, right, compared to the main magnetic field. And what they will do is alter that magnetic field in a certain direction, right, which is why we have three of them surrounding the patient. They have fancy names that I like to joke about. One is known as the X, the Y, and the Z, and they're spaced out in those same coordinates of the patient. So we're going to talk a little bit more about the gradients. We're going to discuss exactly what they do in this slide here, how they affect the precessional frequency, their names again, and what slices they can affect, and a lot about slope. And then we will specifically get into how they do slice selection, how they do the thickness of that slice, the timing of that event, and then we'll switch to phase encoding. We're going to skip frequency and do that last. We'll talk about phase encoding and slope again. Which one does what, we'll get into, because essentially spatial encoding is going to be three things: slice selection, what's known as phase encoding, and what's known as frequency encoding. So let's get back to the top here. What you see here is X, Y, and Z. Our patient's head is over here, feet going through. So their entire body in three directions are surrounded by these gradients. What you have over here, I suspect is supposed to be indicative of the main magnetic field, right? That's the big 1 Tesla, 3 Tesla magnet, whatever you purchased from the manufacturer. That's the one most people think about. But the gradients are multitasking supermen, right? They do a lot of work. So this is a typical illustration of a gradient. And this could be the X, the Y, or the Z gradient. Excuse me. But what they will do is change the magnetic field across the entire patient's body, such that part of the patient's body, so if their head was over here and their feet again towards the left, they are feeling a higher magnetic field towards the right than towards the left. How do we know that? It's color-coded, just as an illustration, but we can see here that it's 1.00 Tesla, 1.005. Here it's just 1, and here it's less than 1 at 0.9995. We see that number converted into Gauss. So if you remember, 1 Tesla is 10,000 Gauss. Here it's 10,005. Here it's 9,995. So the difference here is 10 Gauss across the entire patient's body. So that might not sound a lot, but a tiny little change in the magnetic field that a proton experiences will make it precess faster and slower than a proton that might be just a centimeter away. And the way this works is protons that experience a higher magnetic field will have a higher precessional frequency, and protons that feel or experience a lower magnetic field will have a slower or lower precessional frequency. So let that sink in for a second. What this means is we can control particular areas of the body. So you might start to see already how this can factor into distinguishing one slice from another slice, or putting information into K-space in one place versus a different place, or controlling our bandwidth. So what we can see here is how gradients generally work. They're measured in Gauss per centimeter. So if we use an example of 1 Gauss per centimeter, and that's not necessarily a default number, but it's good as an example, we can see that across just a few inches, right, off of the isocenter, which is the middle, right? So this is known as the isocenter right here. And we can see at the isocenter, we're supposed to be kind of at the theoretical 10,000 Gauss. And we have a frequency of 42.57. Right? That's our gyromagnetic ratio for a 1 Tesla magnet, right? 10,000 Gauss. But when we move just 1 centimeter negative from that, so in this case, we're going this way towards the negative side, right? The textbook that we use kind of gives it a purplish color, but that's just, this one artist. But just that 1 centimeter changes the magnetic field by 1 Gauss, lowering it to 9,999. But the important part is, look what happens to the frequency. You have to keep looking past the first couple numbers, right? Because both of these start with 42, but now we've gone from 42.57 to 42.5657. When we go another centimeter down, it goes 42.5614. So a very small change, but that is more than enough to distinguish these two protons that are a centimeter away from each other. And then the chart just goes on to kind of show you the same thing happens if you go positive. So if we go from the isocenter and positive 1 more centimeter, we go up by 1 Gauss. But notice this goes to 42.5742. We go up 2 Gauss, we're up to 42.5786. And they threw in a bigger jump, right? 10 centimeters negative again this time, but now we go 9,990, right? That's our 1 Gauss per centimeter, so it changes by a factor of 10, and we go way down to 42.52 versus our original 42.57. So all the gradients can do this, whether it's the X, the Y, or the Z. They all work essentially the same way. There are these windings of wire that can be energized and brought to a certain strength. If you remember, that's the term amplitude. That happens over a certain amount of time to go from 0 amplitude to whatever the maximum amount is, the maximum strength. We call that the rise time. How long it can stay on is known as the duty cycle. And the slew rate is a way to kind of encapsulate some of that information so you don't have to look at several different variables to decide which set of gradients you're going to purchase. So again, we have the Z gradient. I'm just going to pause for a moment. So the Z gradient specifically goes from the top of your head to the bottom of your feet, right? So it's the long axis of the body. The Y gradient is going to go from the front to the back, so the anterior to posterior. And the X gradient is going to go across the body from left to right, from shoulder to shoulder, essentially. And that's how we can actually slice and dice up a patient. That doesn't sound good, right? So the Z gradient would be responsible for axial cuts from top down. The Y gradient is going to give us coronal from front to back. And the X is going to give us sagittal imaging. So the Y gradient will not be able to do sagittal cutting, right? They can all do spatial encoding in terms of phase and frequency, but only one specific gradient can do the slice selection, right? And once that is determined, the other two pick up the slack, so to speak, and do the phase and frequency encoding after. So slope, you may have heard of slope. It's kind of the rise over distance, mathematical term. For us, we're really going to think about it in terms of just steep, like walking up a steep hill, or shallow gradient is, a gradual hill, a gradual slope. But it's important because what the slope is, what the steepness of the gradient is, will determine the slice thickness, potentially. For phase encoding, that slope will determine where, in what line of K-space we place information into, towards the top, in the middle, at the bottom. And the frequency encoding gradient's slope will help us determine the bandwidth, right? In particular, the receiver bandwidth, what amount of frequencies we are accepting out of the patient, right? So slope has a factor in all 3 types of encoding, right? We're going to see it again in slice, phase encoding, and in frequency encoding. And what you can see here is we can see that the slope of this gradient can also alter the magnetic field if you have a steep slope. And what this means in reality is we're pumping in more electricity, more energy into the gradient. The analogy I often use is it's kind of like a seesaw, where in this case, I'm pushing down all the way to the ground and the other side is going all the way up. What we see here is a very big difference between the magnetic fields at different sides of the gradient. Here we have 9,700 versus 10,300. That is a 600 Gauss difference, and that is represented as a pretty big difference compared to the one on the right that we'll see in a second. Here we have a frequency of 41.20 versus 43. A shallow gradient is not going to alter those precessional frequencies as much. With this very shallow gradient, right, we have a difference of only 10 Gauss versus, what did I say, 600. We still have a difference in the respective magnetic fields, but now, again, we have to go past the decimal point, 42.54 versus 42.78. So the difference between a proton precessing here versus precessing here is not nearly as much of a difference as a proton precessing down on this side versus all the way up here. So again, we've mentioned this a few times now. Gradients are responsible for size selection, frequency encoding, and phase encoding. It actually is slice selection followed by phase encoding, then followed by frequency encoding. I do need to switch up the slides. I have done that in other presentations. However, I didn't get to doing it for this one. So when the time comes, we'll just kind of skip down and then go back. But the first step is correct here, slice selection. The way this works, if you remember from the beginning how the Lamarr equation works, is when we alter the magnetic field, which our gradient is going to do for us, we are going to then have protons that are, let's say, in a line next to each other. So if we have a few protons from left to right here, that because the gradient is applied across the entire body, again, we don't know whether it's across axial, across sagittal, or across coronal, but they all work the same way. And now we're going to have a situation that different protons in different places will feel a different magnetic field. And because of that, they will precess at a different frequency, one higher or lower than the other one nearby. And this is how we can do slice selection, because what we can do is now decide to target just one area where we know what the new precessional frequency is once we apply the gradient. Lamarr equation then says we send in an equal amount of RF energy such that it matches the precessional frequency. So to say this again, we make sure that we send in a frequency of RF such that it matches the precessional frequency. Once we have that love connection, then the energy will be absorbed. Remember, if we don't have that connection, if we send in a different frequency, or if the frequency that we send in doesn't match the precessional frequency that is there, energy will not be absorbed. Net magnetic vectors of all the tissues will not flip over, and then there'll be essentially nothing to relax or decay, and we won't be able to measure T1 or T2 respectively. So let me see if I can fix this a little bit, because it's kind of dark here. I don't know why. So give me a second. Okay, let's maybe third time is the charm. Okay, last one here. Get it just right, or doesn't like you. So here is what we've talked about, right? So just to review, we have the Z gradient that's going to be axial slices from the top of the head to the bottom. So assuming the patient is, in the MRI machine supine, the X gradient, kind of think across the body. So that goes from left to right. And it is in those exact directions. Z is top down, not down top, right? X is left right, not right left. Y is coronal front to back, A to P, not the other way around. So when it comes to slice thickness, after we've isolated the general area, kind of combined at the same time, we have to think about whether we want a thin slice or a thick slice, right? And we know that how thick a slice is will determine how many slices we're going to get. Also has a role to play in signal to noise. Thicker slices, more signal. But we're not going to get into that too much. We're going to talk about specifically how do you just get a thin versus a thick slice. And there is two ways to do thin and two ways to do thick, right? It's going to come down to what your slope is or a number of frequencies that we send in. So if we want thin slices, we're going to use a steep slope. So it's going to require a lot of energy to get that very steep slope. Or we're just not going to send in that many different frequencies, right? If we send in just a few versus many, we're only going to excite a smaller, thinner set of protons. Whereas it's pretty much the opposite, right? With thick slices, a shallow slope, so that doesn't require as much energy and it's going to be faster to do, or a broad transmit bandwidth. And you can, in some cases, do a combination. So a broad transmit bandwidth is just going to be much or many more frequencies. This won't work in your car. I like to joke that, you can really only listen to one radio station at a time. After all, the RF that we are sending is in that AM radio electromagnetic spectrum. In this case, however, perfectly fine in MRI to send in many stations, right? Of course, if you were trying to do that in your car, your brain would probably fry, but this is just fine in MRI world. So it turns out this is actually kind of a win-win, right? It doesn't take a lot of energy to do a shallow slope, right? You're going to end up with less slices because they're thicker, and you get more signal with thicker slices. So really, this is a win-win-win, right? Thin slices take a longer time to do, and you're going to end up with many more slices. So I love to point out when we have a win-win. So here's just an illustration. We're going to get a thin slice with this steep slope and a much thicker slice when we have a shallow slope applied. Now, when does this happen? This happens in a spin echo sequence. The slice select gradient will go off every time there's RF. Okay. And again, to read these diagrams, kind of start at the top left, and anything happening underneath is happening simultaneously. Then we start to look towards the right. The very next thing to happen is the creation of a free induction decay signal. Remember, generally we don't uh, record that. But then we could see our next step, which is what we're going to talk about next, is the phase encoding. Kind of go back up. Next step is a rephasing pulse. Again, the slice select goes off. Right. Third step, kind of look towards the right. Here's our frequency encoding gradient going off. So that's our third and last spatial encoding step. And it will read out the echo, which is why the frequency encoding gradient, again, we don't know if it's X, Y, or Z in this illustration, is reading out that echo and responsible again for the bandwidth. So we're going to go back to frequency because it's not in the right order and just get to phase encoding. Again, I apologize for kind of having to fix the images here. I think they got corrupted over the last couple of years somehow. So the explanation, the easy explanation here is phase encoding is going to place the echo into a particular line of K-space. And we will have a separate lecture on K-space, but very quickly, you can look at K-space as a big square with 4 quadrants, right? So 1, 2, 3, 4, a top half that's considered positive, a bottom half that's considered negative. And all across we have many, many lines, right? We might have 64, maybe 128 lines, potentially maxing at 256. And K-space is split into a positive top half, negative lower half. And each line has a number where the numbers are low in the center and get bigger if you go positive, but they also get bigger if you go negative. So +1, +2, +3, up to +64, -1, -2, -33, up to -64 for, let's say, a total of 128. Each line is going to contain the information from an echo. How do we decide where each echo is placed? Because one of the things we'll talk about in another lecture is it's important to fill K-space for one, but K-space and where an echo is placed will also determine the contrast versus the spatial resolution ratio, right? When we place information in the middle of K-space, we're going to get more signal. When we place information, the echo that is, towards the periphery of K-space at either end, we get more spatial resolution. But today's lecture is really about how do we just get it in one of these lines, right? And K-space kind of lives in your computer. The illustrations that you may see on the internet or in a textbook, is really just trying to represent memory locations and, somewhere that you can't really touch in your computer, kind of like where is this presentation or where is some Word document, it's in your computer somewhere, right? Which is generally not really that important as long as you can find what you're looking for. So in the case of how do we put a line into K-space, it will work on slope again. If we use a steep slope, when we turn the phase encoding gradient on, when we activate that gradient, it will place information either towards the very top, or if we run the electrical current in the opposite direction, the opposite polarity, it'll put information into the other periphery, right? So it's just either positive polarity or negative polarity. And again, we create this steepness, this slope, by increasing or decreasing the energy that's actually applied to the gradient. So you can see in this way, if we start with a high energy steep gradient and let's say fill the top line of K-space, which might be line number 64, let's say, drop the energy a little bit, we then can fill line 63, 62, 61, etc. And that's generally speaking how K-space is filled, right? There are more than one way to fill K-space, but generally it's a gradual start from the top and we tick down, right? In my kind of analogy from before, it's like pushing that seesaw down to the ground and then lifting it up a little bit at a time, right? So that the other side goes down, 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 down. And that's essentially how phase encoding works, right? Um, when does it happen, right? Again, I'm having a problem with some of my images here. I don't really know why, but we can see if we go back up, right, that it's happening right here, right? So it's the second step, right? And again, if we have a steep encoding step, right, apply a lot of energy, that's going to give us a large phase shift, put us more towards the top. Shallow puts us more towards the middle, but it's step by step in reality. So now we're going to go back. So I apologize for this. We're going to talk about frequency encoding. This is our third step. The frequency encoding gradient, again, could be X, Y, or Z. It depends on which one of those has previously decided that it is going to be cutting for your slice selection. So this generally remains constant in that we keep the same bandwidth and the same FOV, field of view, throughout the sequence, right? The two spatial encoding aspects that change the most is the phase encoding, right? Because that's filling K-space, and that K-space is going to represent one slice. Then the slice selection gradient will change once all the phase encoding has completed. The frequency encoding works the same way, right? It works with slope. However, it's going to determine two things. One, essentially what we're scanning, the field of view, but more importantly, the bandwidth. So if we remember, when it comes to bandwidth, there are two types of bandwidth. There is the transmit bandwidth, what we send with our initial RF, that's our excitation pulse. And then this is the more important one when it comes to frequency encoding, we have the receiver bandwidth. So these are the spectrum of frequencies we are going to accept with which the computer systems will then reconstruct into an actual image. So this receiver bandwidth will have an effect on signal to noise, right? When we have a narrow receiver bandwidth, we're going to have a higher signal, right? What this is here is kind of representative of our bandwidth. So if we have a broad receiver bandwidth, we're getting this entire signal, which includes a lot of noise at the ends. So you might be thinking, you know, why can't I go super narrow and just focus on this one peak in the middle? It's because we need to get a little bit more information than that, right? But it is adjustable. So again, the steepness is going to, or what we call the slope, is going to determine the size of the anatomy that we cover, and it's going to determine to a certain extent what are part of what goes into signal to noise, right? We said signal to noise is affected by not just the bandwidth that we're talking about now, but signal to noise has TR has an effect on signal to noise. When the TR is up, the signal goes up. TE, when the TE goes down, the signal goes up. When the size thickness is thicker, the signal goes up. When the magnetic field is higher, the signal goes up. When the NEX is increased, the signal goes up, not very dramatically, and it takes a lot of time to do so. So this is bandwidth is going to be one part of signal to noise, and how broad or how narrow the frequencies that we accept from the echo go into our overall, or is one part of the many that I mentioned that plays a role in the overall signal to noise. And we can see in terms of timing, it's the last thing to happen, right? Here was the slice, here was the phase encoding steps, and you see the way this is drawn shows you that it's repeating. And as I mentioned, once all of K-space is filled, only then will this slice select change its amplitude, indicating that you have a new slice. But generally speaking, in terms of the frequency encoding, which 1, 2, 3 happens third, and notice we're sampling information from this spin echo, not from the FID, narrowing this in, right? So if we turn this kind of rectangle into a box, would be increasing the slope and getting a smaller slice, so to speak, a more narrow set of frequencies, right? And the frequencies towards the middle are higher, which is why our signal to noise goes up when we reduce this receiver bandwidth. So this is an overall kind of timing of events that we just went over. We start with the slice, we get an FID, phase encoding, we put some information into K-space, rephase, again, this is a spin echo sequence, but generally for gradient sequences, it's the same process. The only difference really, well, there are others, but one major difference is the slice selection gradient is only activated during the excitation pulse. There is no rephasing pulse in a gradient sequence, right? There's a gradient, again, will turn on and off and rephase, right? So again, the gradients are multitasking in many ways. But the gradient for slice select does go off every time in a spin echo sequence, essentially whenever there's an RF pulse, 90 or 180. And then repeats after that. So last few slides, right, just talk about the fact that once slice selection has been determined, which of the two leftover gradients will do the phase encoding and which will do the frequency encoding. You want to read the textbook on this. It's a little complicated. I don't go into it too much, right? Other than this sort of summary slide here. One thing I can tell you is it's based on the long axis of the body, so there's no simple answer in that it depends. I mean, the slice selection gradient is easy to pick out. If you're doing coronals, it's the Y, and that would leave, for example, either the X or the Z to do phase and frequency. And it doesn't work alphabetically. That would be too easy. It's based on the long and the short axis of the anatomy in that type of slice, axial, coronal, or sagittal, that you're cutting. So it really depends on the procedure and what cut you're doing at that time. And also let it be said that this is for, this sort of summary here is for everything except the head, right? Because it doesn't really have a long or short axis. So spherical objects are kind of different when it comes to which gradient does the spatial encoding. When it comes to sampling, basically, I want you to think of Nyquist, right? So Nyquist is a sampling technique, right? When the echo is coming out of the patient, right? So that's that moving magnetic field, and Faraday's law is at play again, which is going to then induce a current in a nearby coil. That information that we get, we're going to sample it and then digitize it Now, do we sample everything? How much can we not sample and still get an image, right? Because sampling takes time. So we generally don't want to sample every single piece of data that we get. So all this is governed by what we call Nyquist. And the rule on Nyquist is we want to sample at least twice per cycle. When we don't, right, that's where we're cutting too many corners and we can get artifacts like aliasing. So if we look at a wave, right, and we see we have one cycle, right, so one wavelength really from the top of one crest to the top of the other, we have data going all along this curve. So this is a little bit simplified, but essentially we need to sample twice. We need to sample all across the bottom and then the top, right? So the troughs and the crests. If we sample only one, so just the tops, that's not enough, right? Nyquist theorem basically says we have to sample twice per cycle. So this is going to be misinterpreted because it's basically a straight line instead of kind of getting all of this. Again, if we sample less than once per cycle, right? So we're skipping. So this looks good at first, right? But notice we skipped versus getting every single one. Again, this can be misinterpreted and we can get a artifact and possibly have to repeat that sequence, right? Adding even more time to an already time-consuming MRI exam, right? But at the end of the day, just remember twice per cycle. I don't expect there to be that many questions on the registry related to Nyquist. And by sampling adequately, and of course, this is built into the system. I don't think you have a way to actually control this, but it could theoretically affect the noise, right? So again, sampling less than once per cycle can lead to, incorrect acquisition of the frequencies, leading to an aliasing artifact. And I think that does it for this lecture. There is a part 2, right, that we will get to next time. Again, bandwidth is in here again. What I didn't mention is that the minimum amount of TE, right, so time to echo, can be affected by the sampling time. One of the things that you need to keep in the back of your head is when TE changes, it will have an effect on signal, right? If it goes up, signal can go down. So in many cases, we want a minimum TE to kind of keep signal high. But also TE has an effect on weighting. So remember, as we start to learn about these different parameters separately, we know that generally changing one thing has this ripple effect that will affect other areas of signal and thus your overall resolution in any given scan. All right, everyone. Sorry I missed class and wasn't able to deliver this lecture live, but I hope it nonetheless will help you just hearing it, and you will have a recording. So if you'd like to listen to things over and over again, that will work. So until next time.